Hello, I'm Yehan Liu, and welcome to my lab5 report, which is about the human rocket. Let's first see some background information. On October 14, 2012, Felix Baumgartner jumped from 39,000 meters, becoming the first person to break the sound barrier in freefall, reaching speeds over 1,342 kilometers per hour. This record-breaking jump combined human daring with complex physics, making it an exciting case to explore high-altitude aerodynamics and the forces involved in such extreme conditions. So my purpose of this lab is to determine the minimum altitude Felix Baumgartner would need to jump from in order to break the sound barrier during freefall. Using a computational model in GlowScript, the lab explores how air resistance, decreasing air density with altitude, and gravitational forces affect his motion. By simulating the descent under varying starting altitudes, the lab identifies the conditions required for Felix to reach or exceed the speed of sound. This lab applies Newton's second law of motion and the physics of drag force. The motion of an object in freefall is influenced by two primary forces, gravity, which accelerates the object downward, and drag force, which opposes motion and depends on air density and velocity. Air density decreases with altitude, reducing drag force at higher altitudes and allowing Felix to accelerate more effectively. The speed of sound, which also varies with temperature and altitude, provides a key benchmark for analyzing his motion. Then let's see some important physical equations involved in this lab. You can see that the first five are the same as we used in lab 2, which is also about the falling object. And the new one is the formula for calculating the speed of sound, since the speed of sound is affected by the temperature. And about the models involved in this lab. Since there was no suitable video to analyze the data with Tracker, I obtained the key data of Felix Baumgartner's jump, such as mass, estimated drag coefficient, and initial altitude from the textual description and video on the official website of the Red Bull Straters mission for use in building a suitable computational model. And the important part, computational model, is a GlowScript simulation developed to model Felix freefall. The simulation incorporated gravity, air resistance, and the variation of air density with altitude. By testing different starting altitudes, the model identified the minimum height needed for Felix to break the sound barrier. And here is a preview of the result of the computational models. So when there's no drag, the minimum altitude to reach speed of sound at ground level is 6,000 meters. And with drag, the initial altitude I get is approximately 6,510 meters. And here are the data I collected from the website and also some video about Felix freefall. So the system is Felix Baumgartner, and the mass also includes his suit and equipment, and the surroundings is air resistance, the drag force, and gravity, and also atmospheric pressure changes. And about the initial conditions and some important data are like system mass, we estimate to be 90 kilograms. And the drag coefficient, typically for a skydiver in a stable position, it is 1.0. And also, like initial position, we determined during simulation, and initial velocity is 0 per second. And the time step we set is 0.001 seconds. These are the codes for the first computational model, and the assumption we made here is air resistance, or the drag force, was assumed to be negligible. And these are the code for the computational model considering drag force, which differs from the previous code in that I manually entered different heights to try to get the final speed in order to minimize the amount of computation, rather than using a loop to try all the numbers in the range. And the assumption we made here is drag force is proportional to velocity. Then here are the results we obtained. The minimum altitude is 6,000 meters when there is no drag, and 6,510 meters with drag. This makes sense because the drag force slows down the increase in velocity. There are really a lot of possible errors in this lab, and I think the most important one that matters the most is the first one, that simplified drag force model, because we assume a linear relationship between drag force and velocity, and this may not reflect real-world conditions where drag force is generally quadratic with velocity. And the answer for the first follow-up question, what does it mean, is modeling drag force as linearly proportional to velocity simplifies the computational framework by avoiding nonlinear effects. This approach approximates the early stage of freefall, However, for high-speed scenarios like Felix free-fall, drag force proportional to the square of velocity provides a more physically accurate representation of air resistance. And for what if air density were assumed constant, the drag force would remain uniformly high throughout the descent, opposing gravitational acceleration more effectively. This would substantially limit Felix's terminal velocity and could prevent him from reaching the speed of sound unless the starting altitude were significantly increased. And thank you for listening.